In this video, we will talk about balancing redox reactions, and these are the topics that we're going to discuss. Before anything else, let us first learn what a redox reaction is. An oxidation-reduction reaction, or a redox reaction, is a chemical reaction that involves the transfer of electrons between chemical species. In describing electron movement in redox reactions, two important half reactions are considered: oxidation and reduction. Oxidation is the loss of electrons from a substance, whereas reduction is the gain of electrons to a substance. Looking at the redox reaction of zinc and copper 2+, we can see oxidation and reduction simultaneously taking place. Here, zinc is losing 2 of its electrons. Thus, we can say that zinc is being oxidized. Since it is the reactant undergoing oxidation, it is also known as the reducing agent, or the reductant, because it reduces the other species by giving electrons. On the other hand, we can see that copper gains 2 electrons. Hence, it is being reduced. Because it is the reactant undergoing reduction, it is also called the oxidizing agent, or the oxidant, because it oxidizes the other species by accepting electrons. For us to easily remember these terms, we can use the mnemonic oil rig, which signifies that oxidation is loss of electrons and reduction is gain of electrons.
Now, in order to keep track of electron flow, we will be using oxidation numbers, which are hypothetical charge values for each individual atom of a molecule. They are not real electrical charges, but rather they are the charges the atoms would have if electrons were not shared but were transferred completely. Oxidation numbers are assigned using a set of rules, which are as follows. Rule number 1. For an atom in its elemental form, the oxidation number is 0. Rule number 2. For a monoatomic ion, the oxidation number is the same as the charge of the ion. Rule number 3. The sum of the oxidation states of all atoms in a neutral species is 0, whereas in an ion, such as a polyatomic ion, the sum of the oxidation states of all atoms is equal to the ion charge. Rule number 4. In their compounds, metals have positive oxidation state, in which group 1a metals have an oxidation state of positive 1 and group 2a metals have an oxidation state of positive 2. And lastly, rule number 5. In their compounds, the oxidation states of nonmetals are as follows. For fluorine, it is negative 1. Hydrogen is generally positive 1 in combination with nonmetals. In combination with metals and boron, it is negative 1. In peroxides, oxygen is negative 1. However, in all other compounds, with the exception of those with oxygen and fluorine bonds, oxygen is generally negative 2. For group 7a elements, they are negative 1 in combination with metals, nonmetals except oxygen, and other halogens lower in the group. At this point, let us now apply these rudimentary concepts in balancing actual redox reactions. To balance redox reactions, two key methods are used: oxidation number method and half reaction method, or the ion-electron method. First, we will discuss how to balance using the oxidation number method. For this method, we will be balancing the reaction of iron 3 oxide with carbon monoxide, as given in the slide. Step 1. Assign the oxidation numbers of each of the atoms in the reaction. For this step, we will be using the rules for assigning oxidation numbers, which we have previously discussed in the earlier slides. Looking at the first reactant, ferric oxide, it is a neutral compound, so its oxidation number must be equal to 0. We know that oxygen is negative 2, and there are 3 atoms in this reactant, so iron must have an oxidation number of positive 3 for everything to add up to 0, in which negative 2 times 3 plus positive 3 times 2 is equal to 0. For the second reactant, carbon monoxide, it is also a neutral compound, so its oxidation number must also be 0. Here, oxygen is negative 2, and so carbon must have an oxidation number of positive 2 to balance everything out. On the product side, iron is 0 because it is a free atom. And carbon dioxide is a neutral compound, so its oxidation number must be equal to 0. Here, oxygen is negative 2, and there are 2 atoms in this product, So the carbon atom must have an oxidation number of positive 4 for everything to be balanced. Next, step 2. Identify the species that are oxidized and reduced. We can do this by looking at the changes in their oxidation number. For instance, we can see that iron is reduced because its oxidation number decreases from positive 3 in the reactant side to 0 in the product side. On the other hand, copper here is oxidized since its oxidation number increases from positive 2 to positive 4. Now, we can observe that the oxidation number of oxygen on both sides remains the same as negative 2. We call oxygen here as a spectator ion, which is an ion that is part of any reactant solution, but it does not participate in any reactions. In balancing redox reactions, we'll be focusing less on the spectator ions and more on the ions that are affected by electron flow. From these changes in oxidation number, we will also do step 3, which is computing the electrons lost and electrons gained. Iron's oxidation number decreases by 3, so there is a gain of 3 electrons. Carbon's oxidation number increases by 2, so there is a loss of 2 electrons. As can be seen, there is an imbalance in electron flow as the number of electrons lost is not equal to the number of electrons gained. Hence, to make this equation balanced, we will multiply the computed numbers by factors to make the electrons lost equal to the electrons gained, and we will use that factor as balancing coefficients. In this reaction, the least common multiple of 2 and 3 is 6, so the oxidation number decrease should be multiplied by 2, while the oxidation number increase should be multiplied by 3. Accordingly, we will also use these factors as balancing coefficients. Here, a 3 is placed before the carbon monoxide and carbon dioxide as coefficients. A coefficient of 2 is also placed before the iron on the product side. There is no need to add a coefficient to iron 3 oxide on the reactant side because the subscript 2 after the iron indicates that there are already 2 iron atoms. And the last step, step number 5. To ensure that we have accurately balanced the equation, we will inspect if the atoms and the charges are balanced for both sides. This table right here displays how the atoms are already balanced for both sides, and the charges are also equal, as can be seen here, in which the net charge on the left is equal to the net charge on the right. There are also 6 electrons lost and 6 electrons gained, so that makes it balanced. Hence, we can say that the redox reaction is now balanced, and this is the final balanced form for the reaction between iron 3 oxide and carbon monoxide.
Moving on to the second method, the half reaction method. This method is particularly used when the redox reaction is expressed with ions in aqueous solutions in either acidic or basic conditions. Let us start to balance an equation in acidic conditions. We will be balancing the reaction of zinc with bromate as given. Step 1. Assign the oxidation numbers of each of the atoms in the reaction. On the reactant side, zinc is a free element, thus having a zero charge. Bromate is a polyatomic ion and the overall charge should be equal to -1. In this ion, the oxygen has a general charge of -2, multiplied by 3 it has a total charge of -6. So to find the charge of bromine, we will add 6 to -1, which gives us 5. Bromine has a +5 charge. On the product side, zinc already has a given charge of +2. The same with bromine, who has a given charge of -1. Since we have identified all the charges, let us proceed to step 2, identifying the species that are oxidized and reduced. The main and only difference between the half reaction method and the oxidation number method is that in the half reaction method, we will split the equation apart into their half reactions. By that, we mean the oxidation half reaction and the reduction half reaction. The oxidation half reaction shows the reactants and products participating in the oxidation process. Since zinc is being oxidized into zinc plus 2, we will have an oxidation half reaction as such. As for the reduction half reaction, we will have a half reaction as shown. since BrO3 minus is being reduced into Br minus 1. Moving on to step 3. After separating the redox reaction into its half reactions, we will first balance the atoms for each half reaction, followed by balancing the charges. The order for balancing the atoms is as follows. Step 3A. Balance elements other than H and O. In the oxidation half reaction, we can see that there is one atom of zinc on the reactant side and one atom of zinc on the product side. Since there is already a balanced number of zinc atoms on both sides, there is no need for further balancing. Likewise, in the reduction half reaction, there is one atom of bromine on the reactant side and one atom of bromine on the product. So there is no need to balance the bromine atoms as they are already equal. Moving on to step 3B. After balancing all the elements other than H and O, we will proceed to balance the oxygen atoms by adding water molecules on the side with the least number of oxygen atoms. Since there are no oxygen atoms on the oxidation half reaction, we can omit this process and go directly to the reduction half reaction. So, on the left side of the reduction half reaction, there are 3 oxygen atoms. So we need to add 3 water molecules on the right side since there are 1 oxygen molecule for each water molecule. Now we can balance the hydrogen atoms by adding H plus on the side with the least number of hydrogen atoms. Since there are 6 hydrogen atoms on the right side acquired from the 3 water molecules, we need to add 6 H plus ions on the left. Moving on to step 4. Now that all the atoms are equal, we need to balance the number of charges by adding electrons on the side which has a more positive charge to balance out the charges. On the oxidation half reaction, the net charge on the left side is 0 and on the right it is plus 2. Hence, we need to add 2 electrons to the right to make the charges balanced on both sides. As for the reduction half reaction, the net charge on the right side is minus 1 and the left a net charge of plus 5. Therefore, we need to add 6 electrons on the left side of the equation to balance out the charges. Moving on to step 5. However, the number of electrons on both half reaction is unequal since there are 6 electrons on the reduction part and only 2 electrons on the oxidation part. Hence, to make the half reactions balanced, we will multiply the computed numbers by factors. In this reaction, the least common multiple of 2 and 6 is 6. So, we will multiply the oxidation part here by 3 to make 2 times 3 equals 6 electrons, while the reduction part remains as is. Or we can say that we will multiply it by 1 to make 1 times 6 equals 6 electrons. Moving on to step 6. We now have 3Zn yields 3Zn2 plus 6 electrons for the oxidation, and for reduction, we now have 6 electrons plus 6H plus BrO3 minus yields Br minus plus 3H2O molecules. Let us proceed to add the 2 half reactions together and cancel the electrons and other substances that are present on both sides of the reaction. Here we can cancel 6 electrons on both sides. After that, we will be left with a redox reaction as shown. And lastly, step 7. Here the atoms and charges have been inspected and are already balanced, so the redox reaction of zinc and bromate is now balanced.
Let us now move on to balancing a basic redox reaction using the half reaction method. We will be balancing the reaction of aluminum with perchlorate as given in the slide. Balancing basic reactions generally follow the same steps in balancing acidic reactions, but after adding H plus ions, we then need to neutralize the H plus ions by adding hydroxide on both sides of the reaction with the same amount for the hydrogen ions. By adding hydroxide, the hydrogen ions and hydroxide ions combine to form H2O, and we will then need to cancel the H2O molecules that can be seen on both sides of the reaction. Hence, similar to the prior method, we will first assign the oxidation numbers of each atom in the reaction. For the left side, aluminum is a free element, thus having a zero charge. Perchlorate is a polyatomic ion, and so its oxidation number must be equal to its ion charge, which is -1. To get this, oxygen must be -2 to have a total charge of -2 times 4 equals -8. So, to find the charge of chlorine, we will equate -8 to -1. This will lead us to have 8 plus -1, which is +7. Hence, chlorine has a +7 charge. For the right side of the equation, hydrogen generally has a +1 charge when paired with nonmetals, and oxygen has a -2 charge. Add them all together, we will have a total of -1 multiplied by 4 yields -4. The overall charge should be equal to -1. So, to find the charge of aluminum, we will add 4 to 1, which gives us 3. Aluminum here then has a 3 or +3 charge. On the other hand, chlorine is a monatomic ion, so its oxidation number must be equal to its ion charge, which is -1. Step 2. Identify the species that are oxidized and reduced. In this step, we will separate the reaction into its half reactions. Firstly, we can see that aluminum lost electrons as its oxidation number increases from 0 to +3. Hence, our oxidation half reaction would be aluminum yields AlOH for negative. On the other hand, we can see that chlorine gained electrons as its oxidation number decreases from +7 to -1. Hence, our reduction half reaction would be perchlorate yields chloride ion. Step 3. Balance the number of atoms and then the charges. First, we will balance all the elements other than hydrogen and oxygen. Looking at the oxidation half reaction, there is one atom of aluminum on the left side and one on the right. Hence, it is already balanced and no further balancing is needed. For the reduction half reaction, there is only one atom of chlorine on the left and one chlorine on the right. So, since all the other elements are already balanced, we will proceed to balance the oxygen atoms. In order to balance the number of oxygen atoms in the oxidation half reaction, we will add 4 H2O molecules on the left side, since there are 4 oxygen atoms on the right. Now, to balance the hydrogen ions, the number of hydrogen ions on the right should be 8. There are already 4 hydrogen ions, so we will only have to add 4 additional hydrogen ions on the right. Now, because this is in a basic medium, neutralization of H plus needs to occur. To do this, we will need to add hydroxide ions on both sides, with the same amount for the hydrogen ions. In this case, we will add 4 OH minus on the left and 4 OH minus on the right. On the right side, the 4 hydrogen ions and the 4 hydroxide ions can combine to make 4 H2O molecules. Notice how we can cancel the 4 H2O molecules on both sides. For the reduction half reaction, we will add 4 H2O molecules on the right, since there are 4 oxygen atoms on the left. To balance the hydrogen ions, we will add 8 hydrogen ions on the left, for a total of 8 hydrogen ions on both sides. Proceeding with the neutralization of H+, we will add 8 hydroxide ions on both sides. On the left side, it can be observed that the 8 hydrogen ions and 8 hydroxide ions will combine to form 8 H2O molecules. Now, we can cancel the water molecules on both sides. So 8 H2O minus 4 H2O will lead to 4 H2O molecules on the left side only, because on the right side, the 4 H2O molecules are already cancelled. Thus, we are left with an oxidation half reaction with balanced atoms as follows. For hydroxide ions plus aluminum yields AlOH for minus. For the balanced atoms in the reduction half reaction, we have 4 H2O molecules plus perchlorate yields chloride ion plus 8 hydroxide ions. Now, it is time to do step number 4, which is to balance the charges for each half reaction. For the oxidation part, the net charge on the left side is -4 because aluminum has a 0 charge and the 4 hydroxide ions have a -4 charge overall. On the right side, it has a net charge of -1 because of the -1 charge of this polyatomic ion. Hence, we will add 3 electrons on the right to balance their charges. For the reduction part, The net charge on the left side is -1 because the perchlorate ion has a -1 charge, whereas the water molecules are simply neutral. On the right side, there is a net charge of -9, brought about by the -1 charge of this chloride ion and the -8 charge of these 8 hydroxide ions. Thus, we will add 8 electrons on the left side to balance it all out. After that, we will proceed to step 5, which is to balance the charges on both equations. Oxidation has 3 electrons and reduction has 8. So we will refer to the least common multiples of 8 and 3, which is 24. Thus, we will multiply 8 on the oxidation half reaction, and we will multiply 3 on the reduction half reaction to get 24 electrons overall. From that, we now have these half reactions in which the oxidation half reaction is 32OH plus 8Al yields 8AlOH4 minus plus 24 electrons. On the reduction half reaction, we have 24 electrons plus 12H2O plus 3 perchlorate yields 3 chloride ions plus 24 hydroxide ions. So we will proceed to step 6, the addition of the two half reactions. We will add these two half reactions together, the oxidation and the reduction half reactions. And we will also cancel out the electrons and substances present on both sides. So we will do that first. As you can see, there are 24 electrons on the left side and there are 24 electrons on the right. So we will cancel these two out. Cancel them and then cancel them. We can also see hydroxide ions on the left and hydroxide ions on the right. So we will also cancel these out. So 32 minus 24, we will be left with 8 hydroxide ions on the left. So we will cancel this, and what will be left here is this reaction. So 8 hydroxide ions from 32 minus 24 plus 12 H2O plus 3 perchlorate plus 8 aluminum yields 8 AlOH4 minus plus 3 chloride ions. So for the last step, step 7, we will inspect if the atoms and charges on both sides are balanced. This table shows us that the atoms on the left equal the atoms on the right, so the atoms are already balanced. These charges also present how the net charge on the left side equal the net charge on the right, in which -8 minus 3 equals -11 is equal to -8 minus 3 equals -11 on the right. Hence, we can say that this redox reaction is the final and balanced form for the reaction between perchlorate and aluminum. So we are done with balancing basic redox reactions using half reaction method. To wrap up this video, we have discussed the key concepts of redox reactions and the rules for assigning oxidation numbers. Along with that, we were also able to identify the oxidation numbers of chemical species, distinguish what is being oxidized and what is being reduced, and we were able to balance redox reactions using the oxidation number method and the half reaction methods for both acidic and basic conditions. That is all for our presentation. We hope you have learned something crucial for this. Thank you for listening and good day.